Okay, I'll just start with an announcement regarding test 1. So you should have got your test 1s back in yesterday's recitation class. If you didn't, I have a few test 1s here that you can collect from me. The average on test 1 was 76. I put the distribution of test 1 scores in an announcement. Here it is, and there's also the link to the test 1 solutions that's in the practice test modules. If you have any questions or queries on test 1, feel free to talk to me or talk to your instructors, recitation instructors. If you have any questions about the grading, let's make sure you talk to me or your instructors about that over the next week. Let's get any grading changes done over the next week. Any questions on all of that? Okay, then I'll move on with the class. In last class, most of last class, we told a tale of two types of circular motion due to magnetic forces. We talked about the circular motion of charged particles in a magnetic field and the special orbits of charged particles in a magnetic field. It actually didn't matter whether they went in big circles really fast or small circles slower. They have a period of their orbital motion. They have a frequency of their orbital motion that just depends on their personality, their charge to mass ratio. So we told the story of that circular motion. Then we also told the story of the circular motion of a square current loop in a magnetic field. We examined the forces and the torques on that current loop. We discovered that if you put a current loop in a magnetic field, it executes circular rotational motion. That's the basis of an electrical motor. So, every home has an electrical motor that's indispensable for us. Your fridge has one. The washing machine has one. We rely on electrical motors in our home. Every car has an electrical motor in it. Not just electric cars, but gasoline cars have electric motors in them to start them up. So we absolutely rely for our everyday lives on electrical motors, and we saw how they work in last class. Today's class, I'm going to move on to the origins of the magnetic fields that we worked with in the last class. I'm going to talk about two tales or two problems in this class. One is going to be the magnetic field of a current-carrying straight wire. An example of that might be a power line that carries power to your home. And then the other thing I'm going to talk about is the magnetic field of a current loop. That might be, for example, the Earth's core is an iron current loop, and that creates a magnetic field. So we're going to talk about the magnetic fields that's generated by, for example, a power line that's a straight current-carrying wire, by a current-carrying loop that, for example, is the Earth's core. We use those results about the magnetic fields of a straight wire and a current loop as building blocks. They're really building blocks for solving other problems. And we'll look at the problem of wires, current-carrying wires attracting and repelling. And we'll also look at the problem of a magnetic solenoid. We'll discuss a magnetic solenoid. And both of those problems are built on top of the building blocks of what's the magnetic field of a straight wire, what's the magnetic field of a looper wire carrying a current. Okay. So let's start with the straight wire carrying a current that creates a magnetic field. What is that magnetic field? If we want somebody to blame for the class, don't blame me for the class. We've got to blame this Danish scientist who was the first to discover that electrical currents produce magnetic fields. And actually, he discovered it accidentally. He was experimenting with electrical currents, and he noticed, it's really lucky, he noticed that a nearby compass needle, it deflected when he switched on and off the currents. So accidentally, Ørsted discovered that electrical currents create magnetic fields by this deflection of a compass needle in a nearby an electrical current. And so our whole class is based on his discovery, basically. After his accidental discovery, there was a lot of activity trying to figure out what the fields of different arrangements of currents look like. So all that activity was what we're going to be doing in this class. What is the field of a straight wire? What's the magnetic field and the magnetic forces of a straight wire? What is the field of a current loop, a looper wire? What does the field look like? What are the forces that it exerts? So this class is exactly about that exploration of magnetic fields, magnetic forces due to electrical currents that was initiated, launched by Ørsted's discovery that currents make magnetic fields. Okay. So I got a slide and a demonstration to show you the magnetic field of a straight wire. And then I'm going to talk about the size of the field, the strength of the field, give you an equation. I'm going to talk about the direction, the orientation of the field. I'll give you another right-hand rule. Okay, so in this picture here on the left-hand side, we have to imagine a straight wire standing vertically is carrying an electrical current that's flowing vertically. And surrounding it, we're using a compass and the compass needle, magnetic compass and compass needle, to map out the magnetic field, because it's sensitive to the magnetic field. What you discover if you do this, and basically this is what Ørsted launched and others did, was that if you take your compass and your compass needle and you move it around the wire, you sort of circumnavigate the wire with the compass, you discover that the compass points along this circular path around the wire. The needle executes little circles around the wire. So that's one thing you discover. Another thing that you discover if you take your compass and move it around the wire is that that compass needle is strongly affected if you've got the compass close to the wire, and it's much weaker in its effect, deflection, if you're further from the wire. So close to the wire, the compass needle is strongly affected by the presence of the current in the wire, and far from the wire, the compass needle is just weakly affected by the presence of the wire. What you're actually seeing through the compass needle is that around the wire is a magnetic field. Around the current carrying wire is a magnetic field. And that magnetic field looks like loops or circles, concentric circles of magnetic field lines that are surrounding the wire and centered on the wire. And those field lines surrounding the wire, those loops of field around the wire, they're closely packed. They're densely packed near the wire, so that's strong field. And they're loosely packed far from the wire, that would be a weak field. And so you can map out the field lines with your compass and your compass needle. Let me show you a demonstration of this. I'm going to put it on a camera so we can see it. This is basically the experiment that Ørsted did and others did about now 200 years ago. So we're basically repeating that experiment. In this setup, I've got a wire here in red. Here it is. And that's a vertical wire, like in the last slide we had a vertical wire. And I can, with a switch, you can't see the switch in the picture, but it's sort of over here. There's a switch, and I can cause a current to flow up the wire or a current to flow down the wire with this two-way switch. So we can do that. There's no current in the wire right now. Surrounding the wire, rather than, no expense spared here, rather than moving a single compass and compass needle around the wire, I've got 4 separate compasses surrounding the wire. And they're sitting in the neighborhood of the wire. Right now, what are they seeing? If you're a compass, what are you seeing right now? What you're seeing right now is the fact that the Earth's a magnet. You're seeing the Earth's magnetic field. So you notice that right now, they're all pointing in about the same direction. It's a direction from over here on the kind of the left, my left of the room to my right of the room, with a magnetic field streaming along that direction. That's the Earth's magnetic field. So that they're seeing the Earth's magnetic field. Now I'm going to close the switch, which will set the current, I don't know which way around this is. One direction will set the current up the wire, and the other direction, if I flip the switch the other way, it'd be down the wire. So let's flip the switch, and let's first turn the power on, and then flip the switch. And you see that the needles react to that. So you're having that accidental moment where you've discovered the magnetic field of a current-carrying wire through its influence on a compass. Now, originally, all the compass needles were pointing in the same direction. Now you notice that the compass needles are at least roughly pointing in a direction that forms a circle around that's centered on the wire. It's not a perfect circle with the compass needles because they're actually seeing both the wire's magnetic field and the Earth's magnetic field. So it's a little bit more complicated, but they reveal the magnetic field around the wire, and they do reveal that it is circular loops of magnetic field. If I were to turn off the current, then the compass needles kind of, we're going to relax back to just sitting in the sofa of the Earth's magnetic field. So they've gone back to pointing from the left to the right of the room. Now if I head the current in the opposite direction, again they form circles around the wire, or approximate circles around the wire, approximate because they're seeing both the Earth's magnetic field and the wire's magnetic field. You might have noticed it looks similar to the last case, but actually if you look at the compass needles, they have a white tip on one end, and that's pointing in the opposite direction now. Approximately the opposite direction, because we've reversed the current, we've reversed the magnetic field, and so we've reversed the orientation of the compass needles that experience the magnetic fields. Okay. I'll go back to the slides. And I've got 2 slides, one a rule about the direction of the magnetic field, the loops around the wire, and one a rule about the size of the magnetic field, the strength of the magnetic field in the neighborhood of the wire. This one's for the direction of the magnetic field. So if you think about it, you've got a current flowing in this vertical wire on the sketch on the left here. We said that the field lines are loops around the wire. Those loops around the wire could be clockwise or counterclockwise. Which direction do the loops around the wire go, given the direction of the current in the wire? There's a right-hand rule, you'll be pleased to know, that tells you the direction of the current around the wire. It's a right-hand rule, again, but it's a somewhat different use of your right hand for this right-hand rule. So let's take a look at this one. This right-hand rule for the direction of the field lines around a current-carrying wire, so it's very specific. This is for the direction of the field lines around a straight current-carrying wire. It says point your right thumb in the direction of the current. So that's the instruction. And so I'm going to point my thumb upwards because the current in the sketch is upwards. Then it says that your fingers curl, or your right hand will curl in the direction of the field lines around the wire. So if you look at my fingers curling around my thumb, they kind of go towards the front of the class over here on the right hand side of my thumb, and then they would return out from the front of the class towards you on the left hand side of my thumb. And that's exactly what the sketch indicates. The thumb is pointing upwards in the direction of the current. The fingers are curling around the thumb. They're curling in the direction of the field lines here. The field lines come out of the screen in this 3D picture. On the left-hand side, they go into the screen on the right-hand side. The fingers come out of the screen on the left-hand side and curl back in on the right-hand side. So this is a very handy way. This right-handed rule is a very handy way of remembering the direction of the current around a long straight wire. What would happen if we reverse the direction of the current? Well, to see what happens if you reverse the direction of the current, that's just changing the direction of your thumb in the right-hand rule. So if I do that, what happens? Now what happens is my fingers are coming out of the screen, or out of the front of the class, towards you on the right-hand side rather than the left-hand side, and they will be going back in towards the screen, the front of the class, on the left-hand side. So if you reverse the direction of the current from current flowing up to current flowing down, you're reversing the curl of your fingers. So rather than the field lines circulating in this direction around the wire, if we change this current to the opposite direction, downwards, we'll change the field lines circulating in the opposite direction around the wire. And the right-hand rule is telling us that. What about the size of the magnetic field? Let's talk about the size of the magnetic field. This little equation here tells you the size, strength, magnitude of the magnetic field. This equation here involves the current that's flowing in the wire. Of course it's got to involve the current in the wire because the current's making the magnetic field. So we expect to see that. And it's in the numerator because more current would make a bigger magnetic field, less current, a smaller magnetic field. Switch off the current, no magnetic field. So all that makes sense. Also depends on your distance from the wire. In the denominator of the equation is r, that's the distance from the wire. That's telling you that if you increase your distance from the wire, then you'll have a weaker magnetic field because you made the number in the denominator bigger. If you get closer to the wire, make r smaller, then you'll increase the magnetic field. That's exactly what we said were the field properties. Nearby the wire, the field was strong, the compasses reacted a lot to the presence of the current. Far from the wire, the field is weak. The compass is just weakly reacted to the current in the wire. And so here's the dependence on current. Here's the dependence on distance from the wire. This guy here, in particular, that mu naught that's sitting there, that mu naught is called the magnetic permeability. That mu naught is equivalent to, like in gravity, the gravitational constant. It's equivalent, like in electricity, to the Coulomb constant. It characterizes the strength of magnetism. If we could, wave a wand to make mu naught bigger, which we can't, that would mean that magnetism is a stronger force. If we could wave a wand to make mu naught smaller, then we would make magnetism a smaller force. But mu naught is set by nature, determined by nature, and it's just a fixed constant that characterizes how strong magnetism is, say compared to electricity, or say compared to gravity. Let's look at an example problem involving what we've just uncovered, discovered, and written down for the magnetic force of a straight wire. We've characterized the magnetic field of a straight wire. We've characterized that field, its orientation, its strength. Let's use those facts. We're going to figure out, actually, the magnetic field that's created in the neighborhood of two current-carrying wires. If you look at this sketch, we've got one current-carrying wire that's carrying a current vertically upwards, here. We've got a second current-carrying wire that's carrying a current horizontally from left to right. Those two wires will both make magnetic fields, and we've got to figure out the resulting magnetic field of those two current-carrying wires. So the way we'll solve this problem is that partly we'll use what we just learned about the current carrying wire of the magnetic field of a single current carrying wire. So we'll use those results, but then we're going to supplement it with an old idea. Remember, you could superimpose electric forces, electric fields, electric potentials. We're going to learn to superimpose magnetic fields, magnetic forces. We're going to use superposition here. So we're going to apply that basic rule about the magnetic field of a long straight current carrying wire to each of these two individual wires, and then we're going to combine or superimpose or add the two magnetic fields of the two wires. So that's basically the plan. I think I'm going to do this on the document camera. So here we are. I made a sketch of the situation. I've got the horizontal current carrying wire here. I call this current I1. I got the vertical current carrying wire here. I call this current I2. We know the currents. They were 7 amps and 6 amps. We were told that in the problem. We know we're interested in a point that is located at the coordinates 4 meters in the x direction, 3 meters in the y direction, from the origin, which is where the two wires cross. So we want to know the magnetic field at this particular point here. So I wrote down all the numbers related to this problem that are on the right hand side. I wrote down the two currents, and I also wrote down two distances. These are the distances, kind of the radial distances I might call them, or the shortest distances between the point, the field point, and the two wires. So this distance here is R1. And this distance here is R2. And R1, that's the vertical distance between the point and the horizontal wire, that's 3 meters, and R2, that's the horizontal distance between the second wire and the field point, that's 4 meters. So that's all the information I was given in the problem. I want to find the magnetic field at that point. Basic idea here, starting idea for me, was that the magnetic field at that location is the superposition of the two magnetic fields due to the two wires. So I'm going to call those B1 and B2, and I've just got to add them up to get the total magnetic field. But I've got to remember that they are vectors. B1 and B2 are vectors. So I've got to handle the addition of vectors. And I'm actually going to do that first. I'm going to write down the answer here, but then I'm going to, I better explain it. I started thinking about the direction of the magnetic fields due to the two wires at that location of the field point, at this point here. And I started to think about what are the directions of the two individual fields at that point, B1, B2, and how they're going to add up to make the resulting field at that point. So let's think about B1. Sorry, let's think about the magnetic field B1, which is due to the current I1. The current I1 in the sketch here is heading towards the right. So I'm going to point the thumb of my right hand towards the right, and my fingers naturally curl in the direction of the field. And so if my thumb is pointing towards the right, the field is coming out of the page above the wire. Is everybody okay with that? So I'm using right hand rule. The field is out above the wire. And so let me just annotate this a little bit. This is out. I called that the positive direction. What about the field of the other wire? The other wire is the vertical wire. So that current is going vertically upwards. And so again, I'm going to use my right hand rule for the field of current carrying straight wire. Pointing my thumb upwards, I discover that we're on the right hand side of that wire. My fingers are curling into the screen. So my fingers curl into the screen on the right-hand side of the vertical current carrying wire. Everybody okay with that? Now, in is the opposite direction of out, which was the field for the first wire. So I've indicated into the page or into the screen with the minus sign here. What I had discovered by using the right-hand rule is that one field was straight out of the screen, and the other field is straight into the screen. They're in opposite directions. And so I'm just going to use plus and minus signs to indicate their directions because they're just in opposite directions. So that's an easy way, straightforward way of handling it. So the plus sign here has the meaning that field is out of the screen. The minus sign is into the screen. Yep.
Yeah, I guess I'm just confused on how B2 is into the screen, because if you hold your right hand like this, your fingers can come towards you with your thumb up. How do you know?
Yeah, so that's a good point. Let me do this and show you. So I hold them like, what you're worried about is holding my fingers like this, with this is the current going up. My fingers are coming out here, but they're coming out on the left-hand side of my thumb. So the field is out of the screen on the left-hand side of my thumb, but where would they go if I curled them around? They would go in on the right-hand side. So that it is in on the right-hand side, it is out on the left-hand side, and sometimes you want to do kind of this business to figure that out. Because, obviously your fingers start on one side and they tend to be on one side of your thumb, but you have to imagine them curling around to the other side.
So you usually go on the right side of your thumb, everything here?
I think it could be either, right? It could be either because, I could have chosen a point anywhere, right? Look at this problem here. There are really 4 quadrants in the problem. And I could have chosen a point in any quadrant, and depending on which quadrant, you'd be wondering about the field above or below, on the left or on the right of your thumb, when you point it in the directions of the currents. Yes?
The point is to the right of the wire, and that's why you're looking at it?
Yeah, that point, 4, 3, is on the right-hand side of the wire.
Okay.
So I'm thinking, which way do my fingers curl on the right-hand side of the wire? Okay, this is a really good, important point to for yourselves, figure out this direction. So that was a good question. Okay, so we've dealt with the directions now. At this point, to figure out the size of the magnetic field, I've just got to fill in the magnitudes of the individual fields. But if you remember, the magnitudes of the individual fields were just that constant. It's written mu naught over 2 pi. multiplying the current in a wire divided by the distance you are from the wire. So here it is for the, let me not write that. Here it is for the first wire. Same equation for the second wire, except it's the second current, and it's that current's distance to the field point, so it's R2. Every number now in this equation, every number on the right-hand side, the two currents and the two distances and mu naught are all known to us, so I can plug them all in. I'm not going to do it, I never do. If I did plug them all in and we waited 10 or 15 minutes for that to happen, what we would get would be the answer to this question. Comes out to be, you can check it, it'd be good too, 0.17 Tesla. It's actually, let me squeeze in a little plus sign, plus 0.17 Tesla. The field due to the horizontal wire is stronger than the field due to the vertical wire. The horizontal wire is carrying more current. That's one reason. The vertical wire less current. They were 7 and 6 amps. But also you're closer, the horizontal wire, you're further from the vertical wire at this particular field point. So there's two reasons that the field due to field B1 due to wire 1 is stronger. The field due to wire number 2, B2, is weaker. And so when you add them, you get a net field. They partially cancel out, but you get a net field that's in the direction of the field of wire number 1. Everybody okay with that? Let's look at a second example. This is the field. This is going to use this field of a current carrying wire as a building block, as like a Lego block, to look at a more complicated problem. Let's see this. We're going to figure out the force, the magnetic force between two current carrying wires using this field of one current carrying wire as a building block. Here's the problem I want to solve here. Yeah. I got two wires. This one upstairs, I labeled that wire number 1. This one downstairs, labeled wire number 2. They have currents I1 and I2. They're separated by some distance. Look, we now know that, for example, wire number 2 creates a magnetic field. Wire number 1 is sitting in that magnetic field. It's going to feel a magnetic force. So there'll be a magnetic force on wire number 1 due to wire number 2. Likewise, wire number 1 creates a magnetic field surrounding it. Wire number 2 is sitting in that field, and so it's going to experience a force. Wire number 2 experiences a force that's exerted by wire number 1. So these two wires are exerting magnetic forces on each other that's mediated by the magnetic fields that are created by the two wires. What we're going to do is put together a result from the last class and put together the result from this class to figure out what that force is between these two wires. So we're going to take this equation from this class. Here it is. That the magnetic field surrounding a straight wire is equal to the current in the wire divided by your distance from the wire times mu naught over 2 pi. So we're going to use that equation that we've just been talking about, and we're going to combine it with the equation for the magnetic force on a straight wire in a magnetic field. It was this equation here that we met in the last class. So we got last class was all about one equation basically. It was the field equation. It was ILB sine theta, or we also used it as QVB sine theta. We're going to use that field equation with a new equation from this class, which is the equation for the magnetic field of a current carrying straight wire. So we're going to combine these two to find out the size of the force between the wires, and we're also going to combine a couple of right-hand rules, you'd be pleased to know, I'm laughing, to figure out the direction of the forces between these two current carrying wires. So that's our task here. I got two slides. One for the direction of the force between the two wires. We'll do that first. The second one for the size of the force between the two wires. We'll do that second. So, direction of the force. So we could do it two ways. We could think about wire number 1 creating a field, figure out the direction of the field at the location of wire number 2, and then figure out the direction of the force on wire number 2 due to that field. Or we can do the way in which I'm describing, is to think about wire number 2 creating a field around it. Wire number 1 is sitting in that field, and we can figure out the orientation of the field due to wire number 2, and then once we got that, we can figure out the direction of the force on wire number 1. So I'm going to take that route, but it was just a choice. So let's start with wire number 2. And this wire is creating, surrounding it, because it's carrying a current, a magnetic field. And actually, there's already a picture or a sketch on here of the magnetic field. It's loops of magnetic field lines around the wire, and they're coming out of the screen upstairs here, and they will be going into the screen downstairs here. And so this is the magnetic field of wire number 2 at the location of wire number 1, due to the right-hand rule for a current carrying straight wire. Let's double check it though, because I might not trust it. I'm going to take my right hand, I'm going to point my thumb in the direction of the current. So the current in wire 2 is heading from the left to the right, so my thumb's pointing from the left to the right. My fingers, we're told, curl in the direction of the circulating magnetic field lines, the loops of magnetic field around the wire. What are my fingers doing? My fingers are coming out of the screen above the wire, and if we were interested in below the wire, they would be going into the screen below the wire. So the field is coming out of the screen above the wire, is going into the screen below the wire, and that's exactly what this picture tells us. The field is coming out of the screen upstairs here, above wire number 2, into the screen downstairs here, below wire number 2. We're just interested in this location. Okay, so we can have a snack. We got the field for wire number 2 at the location of wire number 1 is out of the screen. It's out of the overhead. So given that field direction out of the screen, and given the fact that the current in wire number 1 is heading towards the right, what is the direction of the force on wire number 1? So it is a current carrying wire, it is a magnetic field. What is the direction of the force? This is the right hand rule from the last class, we'll be pleased to know. So how did that one work? Because I'm now using the second right hand rule, I've forgotten the first one. But the way it worked is that you would point the palm of your right hand in the direction of the current. So the current is left to right, so I'm going to point the palm of my hand in the direction of the current. I got to curl my fingers in the direction of the magnetic field. So the magnetic field is coming out of the screen towards you at the location of wire number 1. So how am I going to do that? I mean, my fingers don't want to do it this way. I'm going to have to tip my hand upside down and curl my fingers out. So again, I position my hand so that the palm of my hand is in the direction of the current in wire number 1. The fingers are naturally curling in the direction of the field that's immersed in. My thumb points in the direction of the force on wire number 1. The force on wire number 1 is downwards. It's being attracted to wire number 2. And so that's the direction of the force. So two right-hand rules worked our way from the current in wire 2 through the field of wire 2 through the force on wire number 1, and we find that there's an attractive force. If you did the same thing the other way round, what's the effect of wire 1's field on wire number 2, you'd find it's attractive. Is being attractive too. These forces have got to be equal and opposite. They've got to be an equal and opposite force pair. The two wires are attracting one another. So we've discovered that. What about the size of the force? Well, we combined to get the direction, the right-hand rule from the last class and the right-hand rule from this class. To get the size of the force, you actually combine the equation for the magnetic force due to a magnetic field from the last class with the equation from this class is what is the magnetic field of an electrical current. So we combine the two equations like we combined the two right-hand rules. We're combining this equation from this class with this equation from last class. Now, when I say this equation from this class, I've written it in a way that's appropriate to this problem here. I'm talking about wire number 2's magnetic field. So I put the subscripts 2 on the current and the field. I'm talking about two wires separated by a distance now I've called d. So that r in the original equation is now the separation between the two wires. So I modified this equation a little bit. Likewise, downstairs here, this is the equation ILB sine theta from the last class, but I've also modified it to fit this problem here. I'm thinking about the force on wire number 1 because it's carrying a current. So I put subscripts F1 and I1 to indicate that's the force on wire 1 due to the current flowing in wire 1 as a result of the magnetic field in coming from wire number 2. So I've got a subscript 2 on the B here. So I plugged in these things. I also filled in the fact that theta in this case is 90 degrees. Remember, the field is out of the screen, the current is in the plane of the screen. That's 90 degrees between field and current, so theta's 90 degrees, so sine of 90 degrees is 1, and so I just wrote ILB. Anyway, if you just plug this expression upstairs in equation number 1 into this expression downstairs for equation number 2, you get this result here. And let me focus on this result. This is an equation, it's actually interesting, it's not an equation for the force on the two wires. It's the equation for the force per unit length, the force per meter. So this equation is valid whether you've got two wires that are 1 centimeter long and nearby one another, 1 meter long and nearby one another, 1 kilometer power lines and nearby one another, because it's just telling you the force per unit length on those wires. So it's newtons per meter, yes.
Can you re-explain why we know that we're supposed to do wire 2 field at wire 1 location and not vice versa?
You can do vice versa too. So I could have, let me try this answer. I could have said, let me work out the force on wire number 1. And then I'm going to have to worry about current 2 is making that force. Or I could have said, let me work out the force on wire number 2. If I want F2, then I would have to have worked with current 1 in wire number 1 to find its magnetic field and so forth. So it's just a choice I made to work with wire number 1's force or wire number 2's force. Is that answering your question?
Because one is acting on the other. So
Yeah, one is acting on the other. They're both coupled, they're both involved. But one of them's current is causing the force, the other one's experiencing the force. Yeah.
Thank you.
Okay, so we finally got, I was describing this equation here. Firstly, this is force per unit length, not force. So when we met Coulomb's law, that was force. When we meet this law of attraction, repulsion between wires, it's expressed as force per unit length. But look at the form over here. It says that the force is in proportion to the product of the two currents, I1, I2. the product of I1 and I2. So if you make either current bigger or both currents bigger, you're going to make a bigger force. If you make currents smaller or both currents smaller, you're going to make a smaller force. What counts is I1, I2. That's rather like the interaction of two charges. Remember that Coulomb's law, it was Q1, Q2. Make the charges bigger, bigger force. Make the charges smaller, smaller force. It's the product that counts, and it's the product that counts here. So that's a big similarity between this law and Coulomb's law. This law is called Ampere's law. For charges, it was called Coulomb's law. But they have this same feature that they depend on products of charges or products of currents feeling and exerting the forces. This law depends on the separation of the two wires, and the force goes down with the separation, increasing separation of the wires, but it goes down linearly with the separation, rather than the square of the separation. That was the case of charges. So that's the difference. If you double the separation of the wires for Ampere's law here, you get half the force. If you double the separation of charges in Coulomb's law, you get a quarter of the force. So that is a difference. And also, the other difference is this law involves magnetic permeability that characterizes the strength of magnetic forces. Coulomb's law involved Coulomb constant, which characterizes the strength of electrical forces. Anyway, we've got this result here. Another feature of this law is, look, these are like currents, I would call them. They're currents that are flowing in the same direction. Both those currents are flowing towards the right. Like currents attract one another. If I'd done the problem with opposite currents, one flowing left and one flowing right, we would have discovered by the same procedures that opposite currents repel one another. So the outcome of this study problem is that, firstly, like currents attract one anher, unlike currents repel one another. Compare that to Coulomb's law. In Coulomb's law, like currents repel one another, and like charges repel one another, and unlike charges attract one another. So it's also interesting that this has the opposite behavior in terms of attraction and repulsion. In here, that like currents are attracting and unlike currents are repelling. In Coulomb's law, like charges are repelling and unlike charges are attracting. Okay, let me just demonstrate this for you. If I can. I think I might be able to put this on the camera. Oh, that's bench camera. Why can't I do this? I'm feeling dizzy already from doing that. What are we looking at? We're looking at this box over here. And in this box over here are two wires. You can see them upstairs here. One's black and one's red. And there's an electrical circuit that connects to those two wires such that I can flow a current through the pair of parallel wires. I can flow it in the same direction, and I can flow it in the opposite direction. So I can explore these two cases of the magnetic attraction between current-carrying wires. So I'm going to start with the currents flowing in opposite direction. I'm just putting the switch so that the currents will flow in the red and the black wire in the opposite direction. And we can watch up here, or maybe you can watch down here, whichever you prefer, to see what happens when I switch the current on. Our prediction was that if the currents are opposite one another, that's the current state, the two wires are going to repel one another. So let me switch it on. And look, you see them trying to push each other apart. I mean, they're wiggling to and fro, but they're pushing each other apart from the magnetic repulsion between these two wires. And so we've demonstrated exactly what we computed there. We'll let them settle down a bit. I mentioned that if I leave the switch on too long, these wires start to smoke, and so I've got to be really careful. I was warned about that. I'm going to switch them to the attractive case. This is where the two currents will flow in the same direction. And we're predicting that the two wires will then attract one another, so let's try that. And they attract one another, they're literally stuck together. And so we've again verified our calculation that with like currents, the wires attract one another. Okay, let's go back to class. Yep. And let's just do a quick example calculation. So in this problem, I've got two currents that are flowing in two wires. One is flowing up and one is flowing down, and we're told the two currents, 1¼ amps, 3½ amps. We're told the separation of the wires, 2.5 centimeters, or 0.025 meters, and we've got to calculate the force per unit length between the two wires, the force per meter between these two wires. So I'll do this on the document camera, and this is just a quick, straightforward application of that law, Ampere's law, that we figured out for the force between two straight wires. Here we go. No, here we don't. I made a sketch of the situation, and let's see, the currents were, I1 was 1.25 amps, and I2 was 3.5 amps. And so those are the two currents, and that separation was 2.5 centimeters. Our job here is really just to calculate that force per unit length, newtons per meter, from that equation that we figured out, which is mu naught divided by 2 pi, constant of nature, times the product of the two currents that are causing the magnetic interaction, divided by the separation, greater separation they interact less, less separation they interact more. So all I've got to do is fill in the numbers here. Mu naught over 2 pi. Well, mu naught is 4 pi times 10 to the minus 7, divided by 2 pi, so this is just 2 times 10 to the minus 7. That's the constant of nature. We've got to multiply by the currents, so it's 1.25 amps, 3.5 amps. We've got to divide by the separation, 2.5 centimeters. I want to put it in meters, 0.025 meters. And then if I do that calculation, the answer I got was 3.5 times 10 to the minus 5 Newton meters. That's the force per unit length. These were pretty small currents compared to this instrument over here, the demonstration over here. So the forces were relatively small in this calculation. They were bigger in the demonstration. Any questions on that? Oh, I didn't say these are opposite currents. Opposite currents repel. I'd indicated the force on this left-hand wire being towards the left. right-hand wire, the force being towards the right. They were repelling one another. If they were in the same direction, the two currents, they would have attracted one another. Let's move on to the case of a current carrying loop. Let's take a look at that. I said there were two topics for today's class, right? The straight wire. What's the field of a straight wire, and use that as a building block for solving some problems. Then the current loop. What's the field of current loop? Use that as a building block for solving some problems. I've used up most of the class in the first one, of course, so I'm going to try and speak quickly, maybe. Yes? Yes? Oh, yeah, thank you. Here we are. Two sketches with two pictures of two magnetic fields due to two magnetic arrangements. The one on the right, this is the left, sorry. The one on the left is the field of a bar magnet. We talked about that before. The one on the right-hand side is the field of a current loop. This is the first time we're talking about that. The bar magnet, if you recall, had a north pole and a south pole. Those are human inventions to think of north poles and south poles, but the field lines came out of the north pole, returned to the south pole. They formed loops around through the north pole and back in through the south pole. The field looked kind of like this. It was strong near the magnet and weak far from the magnet. What's really interesting is that a current loop has the same pattern of field. The current loop has what humans have called a north pole and a south pole. The field lines come out of the north pole, they head back into the south pole, and they form loops around the current loop, with the field being strong, the field lines being densely packed if you're near the current loop, and the field being weak if you're far from the current loop. The reason these patterns look very similar is if you could peer inside the magnet, you discover that inside the magnet, within the atoms, the substance of the magnet, there's actually a current loop. There's current loops inside the magnet. And so it creates the same magnetic field pattern as the current loop in the loop of wire that's carrying a current. And so that's the reason the fields look the same, because the origins of the field in terms of currents inside the magnet or currents inside the wire look rather similar. Okay, one slide for what is the size, what is the direction of the field due to the current loop. Let's start with the direction. There's a right-hand rule, you'll be pleased to know, for this too. And you'll be pleased to know it's a different right-hand rule. This one, we're going to use our right-hand rule again. We're going to use our fingers again and our thumb again, but this time for the current loop, you're going to curl your fingers. You're going to start with your fingers. You'll curl them in the direction of the current, and then your thumb will naturally point in the direction of the field at the center of the current loop, or through the middle of the current loop. So in this particular case of this particular picture, look, I got a current that's flowing in this direction around the wire. So it's flowing out of the screen on the left-hand side. It's flowing into the screen on the right-hand side. It's coming out of the screen towards you on the left, away from you into the screen on the right. So let's orientate my fingers in that way. I'm going to have them coming out of the screen on the left-hand side, going into the screen on the right-hand side. So this orientation here, which way is my thumb pointing if I do that? Is pointing straight vertically upwards. The field inside the loop is up. That means that above the loop is kind of the north pole, that's where the field lines come out, and below the loop is the south pole, that's where the field lines will head back in. And so that's the orientation. If I was to reverse the direction of the current, instead of coming out on the left and going in on the right, I reverse the direction of the current. I'd have to reverse the direction of my fingers. They would come out now on the right and go in on the left. Then I would have reversed the direction of the magnetic field. The field would point in the opposite direction. Well, what about the strength? Strength of the field. This is equation we have to be careful with because it's actually only an equation that's valid at the very center of the wire. So it's an equation for the field at the very center of the wire. It's a very specific equation. It tells you the field at the center of the wire is in proportion to the current in the wire. Well, that makes sense. More current, more field, less current, less field. Switch off the current, no field. It depends on the radius of the loop. If the loop is a big circle, then the field's weaker because you're further from the wire. If the loop is a small circle, then the field is stronger because you're closer to the wire. So the field depends on I over A is the radius of the current. There's also multiplied by a constant. Notice here that that constant is different, slightly different for a circular loop of wire compared to a straight current carrying wire. It's not mu naught over 2 pi, it's mu naught over 2. So the fact that the wire, there's a different geometry of wire here, that is a circular loop, rather than the old geometry of wire, straight wire, that difference in geometry causes this difference between mu naught over 2 pi for the straight wire, mu naught over 2 for the circular loop of wire. It just originates, comes out of the geometry. Obviously I'm not explaining how it came out of the geometry. We could do that. We'd be here for the rest of the semester doing it. But it just comes out of that different geometry of circular versus straight wire. Okay, let's look at a little example of this one. We got 2 loops of wire here. This interior one is carrying a current that's clockwise, and this exterior one is carrying a current that's, this interior one was counterclockwise. I don't know which way the clock runs. The exterior one is carrying a clockwise current. So they're both current carrying loops. They're both producing magnetic fields. We want to know the magnetic field at the very center here. We're told the information we need. We need to know the currents in the 2 wires. They're 5 amps and 3 amps. We need to know the fields. The distances, the radii of the 2 wires. We're told 12 centimeters and 9 centimeters. So from that information, we're going to calculate the magnetic field. Now we're going to do this using that rule for the directions of the fields, right-hand rule. We're going to use the equation for the strengths of the fields. That was mu naught over 2 times current over radius. But we've also got to use one additional thing, which is the idea, again, of superposition. There's 2 currents making 2 magnetic fields. We've got to superimpose the 2 magnetic fields to figure out the resulting overall magnetic field. So we've got to do all of that. So let's go ahead and do that. I'm going to do it on the document camera. No. Here's my little sketch. Smaller radius, counterclockwise current. Larger radius, clockwise current. I wrote down the 2 currents, 5 amps, 3 amps. Wrote down the 2 radii, 0.12 meters, 0.09 meters. That's the information we're given. We want to know the magnetic field. Again, the magnetic field, total magnetic field, is the superposition of the 2 individual magnetic fields. I'll call them B1 and B2 due to the currents I1 and I2 in the 2 circular loops. We've got to remember, though, that these magnetic fields are vector quantities. They have size and direction. We have to handle in the addition, their vector nature. We have to handle their directions as well as their magnitudes. So let's start by thinking about their directions. Again, I think I'm going to write down kind of the answer, and then we'll explain it. Current number 1 is circulating clockwise, right, around the wire loop. And the right-hand rule for a wire loop says curl your fingers in the direction of the current. So look, my fingers are curling in the direction of the current. My fingers go clockwise now. And your thumb will point in the direction of the magnetic field. So the magnetic field for current number 1 is into the screen. And so I'm indicating into the screen here with this minus sign. Like I might indicate downwards in a gravity problem as with a minus sign. What about current number 2? Current number 2 is going in the opposite direction. It's going counterclockwise. So I'm curling my fingers in a counterclockwise direction, and my thumb now is pointing out of the screen towards you. So the current's in the opposite direction. We went clockwise to counterclockwise. The field's in the opposite direction. We went from into the screen to out of the screen. So I'm indicating out with this plus sign here. And so this step here is me handling the directions. Because we got two fields that are opposite one another, it's easy to combine the vectors by just using plus and minus signs to indicate the two opposite directions, the in and out of the screen in this problem. Now I've just got to fill in the sizes of the magnetic fields, B1 and B2. There's a common factor when I fill in the sizes, that mu naught over 2. That is in both equations for both magnetic fields. That mu naught over 2 multiplies the current in the wire divided by the radius of the wire. Here it is for wire number 2. Here it is for wire, sorry, this is for wire number 1. Here it is for wire number 2. And then I can just fill in I1 and I2. I can fill in R1 and R2 and calculate the magnetic field. Important, right? The signs are important. You see here that the two magnetic fields will partially cancel out. And one or the other current, 1 or 2, is going to win over the other one. Be bigger. The bigger one, the bigger field, will have the net field in that direction. The smaller one will have end up with the net field being in the opposite direction. Well, if I fill in all the numbers, I'm not going to do it. I'm totally panicked with time. I'm going to pass out, basically. It's 0.52 microteslas is the field. Minus 0.52 microteslas is the field. Minus sign means into the screen. It means that the field of wire number 1, that's carrying the larger current through the bigger radius, is actually bigger than the smaller current in the smaller radius wire. Okay, everybody okay with that? Solenoid. We're going to use the loop, the current loop, as a building block for what we call a solenoid. Solenoids are really important. Every home you have a solenoid. It's also in the washing machine and the fridge and whatever. Your car has a solenoid. Every hospital has a big solenoid that they put people in to do MRI. So solenoids are absolutely everywhere, and they have a very special feature of their magnetic fields that make them super, super special. Here's a solenoid. It's not a difficult thing to visualize. It's actually a collection or a chain of loops of wire. Oh, gosh. Here's a solenoid. It's just a chain of collections of loops of wire, one after the other. So look, let's look on the screen here. This is battery and this is stopped. Maybe not. Here's the first loop, second loop, third loop, and so on and so forth. So we've just strung together like Christmas lights loops of wire to turn a single loop of wire into multiple loops of wire that we give a name as solenoid. The solenoid, a solenoid, is characterized by some numbers that reflect the geometry, the construction of the solenoid. How many turns, how many loops of wire, that's the uppercase N. The radius of the solenoid, that's the lowercase r. The length of the solenoid, that's the That's the uppercase L. That describes the geometry of the solenoid, and then in operating the solenoid, you would describe the current that you're flowing through the windings of the solenoid. So here's the amazing bit. And this just seem, to me, it just seems amazing. How does this happen? You start with a single loop of wire that has a field that comes out of the center of the loop of wire. We've got an equation for the field at the center of the loop of wire, but we don't have an equation for the field everywhere else within the loop of wire. It's not mu naught over 2 times I over R. When you put a stack, a chain of loops of wire together, what miraculously and beautifully happens is you create inside that stack of loops of wire a uniform magnetic field everywhere throughout the volume. This is how you make a uniform magnetic field. We learned how to make uniform electrical fields with charged plates. Well, if you want to make an equivalent uniform magnetic field, you use a solenoid. This is a picture of us putting together a solenoid by winding up the solenoid here and putting the loops of wire closer and closer together. This over here on the right is when we finished building our solenoid, and we've got this closely stacked arrangement of loop after loop of wire. The field inside the solenoid is given by this equation upstairs here. It can be written in two different ways, and it's equal to mu naught. We'd expect to see that, right? It's a magnetic device. It's going to involve magnetism. So it's going to involve mu naught. It involves the current that's flowing in the solenoid. It better involve that. Won't get any magnetic field if we have no current. The bigger the magnetic field, the stronger the current. And then it's just multiplied by a geometrical feature of the solenoid. It's N over L is the number of turns per unit length. The number of loops of wire in your solenoid divided by the length of the solenoid. We sometimes write that in a more compact fashion, not as uppercase N or uppercase L, but rather as lowercase n, meaning the number of turns per unit length. So lowercase n is simply uppercase N over L. That's the field inside the solenoid, and that's the field. That's this incredible field that is uniform throughout the volume of the solenoid. And it's how you make a uniform field. Quiz question. I'll end on this quiz question. And it's about the solenoid. And you can think of it in terms of the equations for the solenoid, our understanding of the solenoid. Let me publish this. We're asked to think about two solenoids, the one on the left and the one on the right. We're told that the two solenoids have the same length, both uppercase L. They have the same number of turns, uppercase N. So they would have the same number of turns per unit length. We're told that the two solenoids carry the same currents. They both carry current I. But the two solenoids do have something that's different. It's obvious in the picture. One of them has twice the radius, one of them has half the radius of the other. So this B has twice the radius, A has half the radius. How do the magnetic fields in the two solenoids compare? Is A's field larger, smaller, or the same as B's field? So that's the question. The answer is that they have the same fields. One way of thinking about them having the same fields is that the field is mu naught I lowercase n. There's nothing different for the two solenoids in their mu naught, nothing different in their currents I, and nothing different in their turns per unit length. So the fact that one is big and one is